To help supplement the identities and formulas from the last video, I'd like to consider the following. We're going to define parametrically. X is going to be equal to 5 times the cosine of t, and y is going to be equal to 4 times the sine of t. I'd like to do the following three things. Determine the equation of the tangent line to the parametric curve at t is equal to pi over 6. I'd like to determine the concavity at t is equal to pi over 6, and I'd also like to eliminate the parameter from the original two equations. So we will do these one at a time in the order listed. For part A, in order for us to determine the equation of the tangent line, anytime we want the equation of any sort of line, we're going to need two things, a point and a slope. So let's start with a point. To get a point on the line, that'll need to be in the form xy, which for us, according to what's been given to us, is going to be 5 times the cosine of t and 4 times the sine of t. And we'll go ahead and plug in t equals pi over 6, and we will get that the ordered pair is going to be 5 times the cosine of pi over 6, comma, 4 times the sine of pi over 6. Simplifying those according to the unit circle, cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is going to be 1/2. Therefore, our ordered pair is going to be 5 square roots of 3 over 2, comma, 2. Now that we have the point, let's get around to finding a derivative. So for the slope of the tangent line, we are going to need dy over dx, which is going to be dy over dt divided by dx over dt. Now dy over dt, that's going to be the derivative with respect to t of 4 times the sine of t. And we'll put that over the derivative with respect to t of 5 times the cosine of t. Evaluating those two derivatives, we're going to get 4 times the cosine of t over negative 5 times the sine of t. Now, we could simply leave it in this form, or in anticipation of things to come, we could also refer to it as negative 4/5 times the cotangent of t. Now, this is just what dy over dx is equal to. It doesn't become a slope until we actually plug in the given t value. So, dy over dx evaluated at the given value of t. This will probably be easier to understand if I'm plugging t equals pi over 6 into this expression. So let's go ahead and do so. 4 times the cosine of pi over 6 divided by negative 5 times the sine of pi over 6. Plugging in those two ratios from what we had earlier, this will be 4 times cosine of pi over 6 is root 3 over 2. And in the denominator, this will be negative 5 times the sine of pi over 6, which is 1/2. Simplifying both the numerator and denominator here, this will give us 2 square roots of 3 divided by negative 5/2. We can turn that into multiply by the reciprocal and call this 2 root 3 multiplied by negative 2 over 5 to get a final slope of negative 4 square roots of 3 over 5. That's already starting to look much better. Once we have our point and our slope, we can take those two things and put them into point-slope form. Y minus y1 is equal to m times x minus x1, which yields y minus 2 is equal to our slope, negative 4 square roots of 3 over 5, times x minus the corresponding x coordinate of the point. Now, as far as I'm concerned, that's looking just fine as far as the final answer is concerned. Of course, if you're interested, you could turn this into slope-intercept form by saying let's distribute this to both terms. Get y minus 2 is equal to negative 4 square roots of 3 all over 5 times x. Oh boy, alright, minus a negative. We can get the 5 and the 5 to cancel. 4 over 2 would be 2, and root 3 times 3 is 3. 2 times 3 is 6. That turned out surprisingly well. Or finally, we could say y is equal to negative 4 square roots of 3 over 5 times x plus 8 by adding 2 to both sides. That turned out remarkably well. Next thing I'd like to do is take a look at part B, where we're going to evaluate the concavity at t equals pi over 6. However, because we're a little bit low on space here, I just wanted to call back to this guy right here. This is what we got for our first derivative, negative 4/5 times the cotangent of t. So, for part B, the concavity. In our last video, we said that d squared y over dx squared is going to be equal to the derivative with respect to t of whatever we got for dy dx divided by dx dt. Now, these were done on the other page, so once again, little reminder. The first derivative was negative 4/5 times the cotangent of t. Negative 4/5 times the cotangent of t. And this is all over dx dt. And x, if I recall correctly, is 5 times the cosine of t. Yes, indeed. So 5 times the cosine of t. Negative 4/5 is a constant multiple. We don't need to worry about that. Derivative of the cotangent of t is going to be negative cosecant squared of t. And in the denominator, 5 times the cosine of t will become negative 5 times the sine of t. Now, as a reminder, the cosecant is the reciprocal of the sine. And when we're dividing by this negative 5, it's like saying multiply by negative 1 over 5. So when all is said and done here, we are going to wind up with negative, negative, negative. 4 on the top, 25 on the bottom. And a total of 3 sines in the bottom. So that'll be sine cubed of t in the denominator. Now we were interested in evaluating this concavity at t equals pi over 6, so let's go ahead and do so. D squared y over dx squared evaluated at t equals pi over 6. It's going to give us negative 4 over 25 times the sine cubed of pi over 6. Sine of pi over 6, which we've done a couple times, is going to be 1/2. When we cube that, we're going to wind up with a 1 over 8 in the denominator, which can head up to the numerator as a factor of 8. 4 times 8 up top is going to give us 32. Denominator stays 25. And we'll throw a negative sign in front to make sure that we know that this thing is concave down. Now, to get a better idea of what this thing actually looks like and what we just calculated, what I'd like to do is eliminate the parameter. So first things first, let's recopy down our original parametric equations. It was x is equal to 5 times the cosine of t, and y is equal to 4 times the sine of t. Now what we're going to go with to relate the sine with the cosine, as I mentioned in one of the earlier playlists, when it comes to conic sections, try to isolate the sine and the cosine, and then apply a Pythagorean identity. So this would be that the cosine of t is equal to x over 5, and that the sine of t is equal to y over 4. Then if we apply the Pythagorean identity, which states that the cosine of t cosine squared of t plus sine squared of t is equal to 1, squaring the x over 5 will give us x squared over 25, plus squaring the y over 4 will give us y squared over 16 is equal to 1. This is the equation of an ellipse. Now, this is an ellipse that'll extend 5 units horizontally, 1, 2, 3, 4, 5, and 4 units vertically from its center at the origin. 2, 3, 4, 5. Now 1, 2, 3, 4. Alright, so I'll try to make this kind of football shaped. I always love that it's called football. Really, it should be called hand egg. Now the point that we were referring to was the point in quadrant 1 where the y-coordinate was 2, so that's going to be right about here. To get the slope of a tangent line, we would need a straight edge, and all of my rulers are on campus, so that's not going to happen. So here is our tangent line that we had. And our concavity is also going to be concave down. The trick for concavity is to curl your fingers in the same direction as the curve of the actual curve. If your palm faces down, it's concave down, and if your palm faces up, it's concave up. In this case, we can see that the palm faces down if we curve our fingers in the same direction as the curve over here, which is why the negative concavity certainly makes a whole lot of sense. So hopefully this little visual aid at the end helps out a little bit. If not, you can use a piece of graphing software to help you out.